Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 14.7, day 2, entitled Introduction to Statistical Thinking. And today we're going to finish up this section by talking about sample size and margin of error, and then what it means to be two variable data, or to collect two variable data. Now, when we're dealing with our sample size and our margin of error, one of the most important features of statistical thinking is the realization that statistics does not prove exact answers. Statisticians estimate properties of a population by examining a random sample from that population. So statistical conclusions are based on the probability, and they always have to be accompanied by a confidence level. Now, a 95% confidence level means that there's less than 5% chance that the results obtained from the sample could be obtained by chance alone. So in the popular press, poll results are accompanied with a margin of error. That's how we refer to that confidence level. So here, if you say that a recent poll shows that candidate X has 57% of the vote, and here it was conducted among a random sample of 600 registered voters, and the margin of error is plus or minus 3%. So that means that 57% could have confidence in this candidate, or it could be 3 less than that, so it could be 54%, or it could be 3 more than that, so it could be 60%. So the confidence level is really in between those values. Okay. So in general, the proportion, p sub 0, of individuals with a particular characteristic in a sample is an estimate of the true proportion, p, of such individuals in a population. So it's clear that the larger the sample size, the more accurate the estimate is likely to be. So that's important. It's in bold there. And we're going to refer back to that concept at the end of the notes as well. So the margin of error is an estimate that's associated with the sample, and it's a number, d, that satisfies the following. So you have to have a 95% probability that this interval, so that's that proportion or that percent that you have, and then plus or minus that confidence level or that margin of error. Okay, so this interval then, this is a mathematical interval. This is our interval notation. Okay, like I wrote, oh, where'd it go? Right here. I could write this as an interval. I could say we want everything from 54 up to 60. Okay, so that's really the 57 minus 3 all the way up to the 57 plus 3. So that's the interval notation that they're using here. Now in that interval then, that is where I have to contain the actual result. So if that interval contains the actual results with a 95% confidence, that's what we want. So this is our calculation to find our margin of error. So we're going to take 1.96 and we're going to divide it by 2 times the square root of the number that we have in our sample size. So n there is our sample size. So that's going to help us find the margin of error. So that way we can find that confidence interval. Okay, so we're going to do that here for example 5. Okay, so a political poll is conducted to gauge the approval rating of candidate X. A random sample of 600 voters is polled. The poll indicates that 324 of those surveyed approve the candidate. So for part A, we're going to estimate the percentage of voters in the population who prefer the candidate. Well, we'll just take 324 and divide it by 600. Okay, so that's going to be 0.54 or 54%. So then we're going to find the margin of error. So this is the formula that we saw on the previous screen. So we'll calculate the value for D. So we'll take 1.96 and we'll divide it by 2 times the square root of the number of people who were polled. So that's 600. Now remember your order of operations here. You have to do the square root of 600 and then times it by 2. Then take 196 or 1.96 and divide it by that number. And you should get 0.04. So that means our margin of error, if we make it a percent, it's really plus or minus 4%. So now we're going to state the confidence interval. So that means we want to go up 4% and down 4%. Okay? So we can think of it in terms of a decimal, or we can think of it in terms of a percent. We could take the 0.54 and subtract the 0.04, so we would get 0.50. And then we could take the 0.54 and add the 0.04, so we get the 0.58. So we could write our interval that way. Or you could just say it's between 50% and 58%. Okay, so somewhere in between there, that's that interval where the true percentage actually lies. Because there's always a chance that you could get these numbers by chance. Okay. So now let's talk about our last concept, which is two variable data and correlation. And up until now, we've studied one variable data. That's where we talk about one property, like we measure somebody's height. So two variable data, which is where we measure two things, two properties. So we could measure somebody's height and how much money they make. Okay. And then we want to see if there's a relationship between those two characteristics. And we can do that by, I think it starts over here. We can record somebody's height and salary. So we can collect that from a group of individuals. And then our goal is to discover whether or not there's a linear relationship between the two variables. Okay. So we would want to then make a scatter plot with that information. So on one of our axes, we would have their height, and on the other, we would have their salary. And then when we plot those points for every individual, it'll make a scatter plot, which you've seen ever since you were in middle school, so you know how to do that. And then we would analyze it by finding the line that best fits that data, the line of best fit, or the linear regression, the regression line. Now, associated with regression, the regression line is a correlation coefficient, which is a mathematical measure of how well the data fits along the regression line, or how well the two variables are correlated. And we need that correlation coefficient to be between -1 and 1. Now, here in this top paragraph, it says that if that coefficient is 0, then that means that there's little correlation. So it's not statistically significant. But the closer that number gets to 1 or -1, the more statistically significant it is. Now we want it to be closer to 1 or -1 depending upon the slope, because we could have a relationship where it has a positive slope, or we could have a relationship where there's a negative slope. Okay, so it depends on the situation if it's +1 or -1. Okay, now the bigger the sample size, right here is where they're talking about this. The bigger your sample size, the more likely you're going to get an accurate representation. Okay, so we need to make sure that we have, if I go to this chart, when we're dealing with smaller numbers that we're sampling, we're going to have a bigger value for R, that correlation coefficient, to show that it's statistically significant data. But the more we sample, that number actually goes down because as we sample more and more and more, we're going to get more accurate results that are going to truly reflect what's going on with the entire population. So you see, as we get to 80 and 90 and 100, we're already down to 0.1. So if you sample 100 people, then to show that your data is statistically significant, you need a correlation coefficient of 0.197. That's it. But if you sample 5 people, you need a correlation coefficient of 0.878. So that's a big difference. So you want to sample more people, so that way you have to have a smaller correlation coefficient to show that your information is statistically significant. Okay, so that's just a further elaboration of what I explained. Okay, so let's look at our very last example here. A student wants to test the relationship between study time and blood pressure. So this table gives the data the student obtained. Okay, so we have 5 data points. So that's not much. So if we're looking back on this table here, we're going to be dealing with 5 pieces of information. So we need a correlation coefficient of 0.878 in order to be significant. Now, I'll show you this more in class. I wish I had that feature on my oh, you know what? Hold on. Let me pause this for one moment, and I'll pull up the calculator on the laptop, and I'll just show you right here.
Okay, so now I have pulled up the graphing calculator feature here. So I'll show you how to put this table into your graphing calculator. So we have 5 data points that we have to put into the calculator. So we want to first put that in, and we have to go to the stat option, and then we're going to go over to edit or select edit. So you can just hit 1 or you can hit enter, and then you have to type in all of the values. So I've already typed them in, and you can just arrow over, and then you can type, and you can hit enter, or you can arrow down. When you get the first list in, just arrow over and then type in the second list. But make sure that you have the same amount of data points in each list. Make sure that you're not missing one, because otherwise the calculator can't graph it properly. Okay, so next we're going to graph it, and my graph is actually going to show the line because I've already typed that in. But if you haven't graphed it yet, you have to go to second and then y equals. So you go to your stat plot, and you can hit enter and make sure that it's turned on. If it's not turned on, hit enter again so that it will be turned on. And then you want to make sure that the type is the scatter plot that's selected. Now the first time you graph, you want to do zoom, and then option number 9, that's for your scatter plot. Now you won't see the line that's going across there. I've already put in my linear regression line. You'll just see your 5 points there. 1, 2, 3, 4, and 5. Okay. So to get the line, we're going to go back to stat, and this time we're going to go over to calc, and we're going to pick option 4. We're going to have the calculator do the linear regression line for us. Okay, now it'll say that it wants to take the information from list 1 and list 2, which we want, and then the other stuff you can leave blank, but at the very bottom there it says calculate. So you have to arrow down to calculate and then hit enter, and it spits out the information for you. Now this is y equals mx plus b form, but the calculator's programmed so that it's y equals ax plus b. I don't know why they do that. So you have to jot down those values so that you can put that into an equation, and then we'll put it into slope-intercept form and put it in for y equals. So go to y equals, and then you put in that equation, 1.09x plus 1.24.75. So you substitute in the values for a and b, basically. Then if you hit graph again, it'll show the line for you. That's when your line will show up. And you can do that just so you can see how closely it is to your data. It's good to do that and double check it, because sometimes you enter something wrong and the line looks really funky, so that's a good double check. Now, the last thing we need then is our correlation coefficient. And again, the calculator will do that for you. Depending on what version of calculator you have, you might have to select a different option here. So go to the Stat menu again, and we're going to arrow all the way over to Test. And then if you have an 84, you're going to go to option G, and I'm going to arrow up because that's actually faster to get to option G. And if you're in the TI-83, you're going to want to go to option E. But we are looking for this linear regression T integer. So it says lin reg T int. That's the one you're looking for. So Casio people, I apologize. This is all being done on the TIs. So we'll have to help you out in class. But hit enter and it'll go into this screen here. It'll say, do you want me to take data from list 1 and list 2? Yes. And here's your C level, that confidence level, the 95%. We want that. So then we're going to go all the way down to our calculate. And we could put in our regression equation if we wanted to, but we don't have to. You can go down to calculate, hit enter, and you get this screen. And at first you're like, oh no, it doesn't have my data, but it's got this little arrow here pointing down. So if we arrow down, it shows us the rest of our data. And the value we need is the very last one. It's R. So 0.564 is our value that we're looking for. So I'm going to go back here now, and I'm going to
Type in or write in my value. So R equals 0.564. Okay, and then the next thing it wanted us to find was whether or not that data is statistically significant. So, like I said before, for 5 data points, we need to have an R value of 0.878, and we didn't get that. So, no, it's not statistically significant. Okay, so here again, this just explains use your calculator to find the R value, and that's what they found, and it's less than the 0.878, so no, it's not statistically significant. Okay, so here's the last homework assignment then. Most of the problems are odd, so you can check them in the back of the book. It's all worked out on the class website. If you have calculator questions or questions about how you put this into your calculator, definitely come on in and see me before school.